Are you able to see? Are you able to see my PPT?
Yes, sir.
Okay. My audio is clear, na?
Yes, sir, it's clear.
Okay. So this is what problem we are going to discuss today. A liquid is flowing in upward direction. Okay. So liquid is flowing in upward direction. The previous problem was gravity was supporting the direction of the flow. Gravity was supporting the flow. Here in this direction, gravity is opposing the flow. As we are moving up, a potential head is increasing. Okay, we'll be using some pump or anything, any other thing to add this pressure actually, so that there will be flow in upward direction under the influence of pressure and the gravity. Gravity is opposing in this guy. In an annular region between two coaxial cylinder, a radius is kappa r and r. Inner radius is kappa r and outer radius is r. Consider a steady state laminar flow of the fluid with a constant density and viscosity mu, vertical tube and length L. So, and radius R. Develop the equation for flux profile, velocity profile, average velocity, maximum velocity, mass flow rate and drag force on a tube. Both tube and single tube also. Inner tube also you can calculate drag force. Outer tube also you can calculate drag force. So that you can add together, that will give you a total drag force acted on a total both inner tube and outer tube. So this is what pictorial representation of the problem. So here we have outer cylinder. Okay, this is outer cylinder. So this is outer cylinder. Okay, and these are the boundaries of outer cylinder, and this is inner cylinder. This is inner cylinder. This is the boundary of inner cylinder. So we are discussing flow in this region. The space between inner cylinder and outer cylinder. We have already discussed the flow through pipe. That will be if we are say in shell and tube heat exchanger, we'll have both flow. One flow will be flow through pipe, another flow will be flow through shell. So this is kind of flow through shell. So how to get the velocity profile for flow through shell? That is what we are going to discuss in this problem. And this problem already we have discussed. So here one difference is this annulus is there. Okay, we are discussing the region between these two cylinder, and secondly direction of flow is against the gravity. Direction of flow is against the gravity. So certainly this gravity is opposing the flow. It is opposing the flow. So, and this flow, there will be steady state, constant density, constant viscosity system. Flow is steady, so velocity is constant with, and it is not changing with time. So certainly I need to add some pressure. Most commonly pumps are used to add the pressure. Okay, pumps are used to add the pressure so that there will be flow in this direction. And as I am moving up, the potential head, here potential head initially will be lower, and potential head of the liquid molecules is increasing. Potential head, as height is increasing, potential head is increasing. So pressure is adding some of the pressure also, and that will be equivalent to gravitational potential head. That will be lost. Some of the pressure will be lost against the gravity also. So what kind of this thing coordinate system will be useful here? Roll number 180, Anuja.
Yes, sir.
What kind of coordinate system will be useful here?
So cylindrical coordinate system.
Cylindrical coordinate system. Where will be the origin?
So it could be on the either of the sides, either bottom or top.
Okay, bottom where?
Yes.
Bottom surface,
The
top surface, where it
center.
will be? It
Center.
will be center. Now you can see here. Here I'm discussing the flow here and here. So still I am taking the origin here. So origin can outside the my system also. Here I don't have my system, okay. Here I don't have my system. Here I don't have my system. My system starts from outer surface of the inner cylinder to inner surface of the outer cylinder, and I am selecting the origin here because there are only two options. So which will be better, Anuja? Whether this will be better or this will be better? Anuja,
Yes, sir.
so which will be better?
So the bottom one.
Bottom one. Why?
So because we have the flow in upward direction.
Yeah. So my Z axis will be parallel to direction of flow. Okay. Z axis will be parallel to direction of flow. So I will be using cylindrical coordinate system. Okay. And this cylindrical coordinate system origin will be here. So this is Z. So the boundaries of the Z will be Z varies from 0 to length of the tube. Say L is the length of the tube. And this R varies from 0 to not 0. R varies from kappa R to R. Okay. Z varies from 0 to L. Okay. 0 to L. Z varies from 0 to L. But R is starting at kappa R. This is outer diameter of the inner cylinder is kappa R. K is between 0 and 1. Kappa capital R, and this is capital R. This radius of this outer cylinder is capital R, and this will be kappa R. Kappa R is less than 1, greater than 0. So this R started at kappa R and ends at capital R. Kappa capital R, and say this is say radius, outer radius is say 1 meter. So inner radius is 0.75. So it will be 0.75 times 1. Okay, 0.75 times 1. So this is say 1 meter. So this will be 0.75 meter. This can be anything. This derivation is true for all values of this thing. Inner radius varies from kappa should be greater than 0. It should not be equal to 0. If it is equal to 0 means there is no inner cylinder. Okay, kappa equals to 0. So no inner cylinder, it will be equivalent to flow through time. That will be limiting cases you should get actually. If kappa equals to 0, this whole derivation will reduce our this thing to this thing actually flow through pipes. So kappa should be greater than 0 and less than 1, kappa r. And what is theta? Theta is total. You can see total theta is there. So theta 0 to 360. Theta 0 to 360. So R, theta and Z. So these are the boundaries of my flow through annulus. This is clear to everybody? Roll number 115 Palak. Roll number 115 Palak. I'm not able to hear you. Roll number 117 Shashwat. Shashwat. Roll
Sir?
number, yeah, Palak. Palak.
Yes, sir.
Yeah,
Yes,
yeah.
sir.
So, can you expect some what kind of velocity profile you will be getting? What kind of flux profile you will be getting? Expectation is very, very important. Before going into model equation, so you should expect what kind of velocity profile I am getting here. So, what
Yes,
kind of
sir.
velocity profile is expected?
So like the pipe, flow through pipe condition, something like that.
Something like that means, can you just tell me exactly where will be minimum
Okay, so
velocity?
okay, so flow through pipe, the velocity profile was parabolic.
Uh-huh.
and the flux profile was something like linear distribution.
Okay. And
So,
here,
so
where you will get zero velocity first of all?
sorry, sir.
Where you will get zero velocity?
Ze- Zero velocity. So here it won't be symmetrical, as in case of the flow
No,
through
it will
pipe
be
condition.
symmetric around theta.
Yes, sir.
Symmetric around theta.
Yes,
So
sir.
where you will get zero velocity?
So at R is equal to kappa R.
Kappa r, that is only one zero velocity you will get. So
Yes, sir.
here you are telling.
And at R is equal to capital R also.
Okay, so here also velocity is zero, here also velocity is zero. So no slip boundary condition. No slip
Yes, sir.
boundary condition. So velocity will increase and decrease. This is the
Yes,
kind
sir.
of velocity profile you will expect. And where will be a maximum velocity front?
So at the center, like center of the hollow part.
So do you expect that it will be at the center?
Yes, sir.
Okay. How many of you expect that maximum velocity will be at the center of kappa r and r here at the center? Can you write in chat box?
So actually, I think not at center, but somewhere between.
Somewhere between. First of all, let me know how many of you think that so maximum velocity will be at the center. Somewhere in between. The center is also in between only, na? So somewhere in between. So whether it is at center or any location other than center. Nobody thinks anything. You write at center or not at center. Are you able to hear me all? At the middle of both pipe, not at center, at the center, not at center, at center, the center, at center, not at center. So it is all together okay. You can say mixed answer. Some people are answering at center, some people are answering not at center. Somewhere between not at center, not at center. Yeah, roll number 50, Rashmi.
So,
Yeah, you have given that it is not at center.
sir, actually, with respect to R, it's not symmetrical. Like once we get the equation, we can differentiate and see like where we get maximum.
Okay, okay. So with respect to R, it is not symmetric. Okay, this is your answer. Why it is not at center? Any other logical answer?
So no, sir.
Not at center is correct actually. Roll number 2, Abhishek.
Yes, sir.
Yeah, why it will be not at center?
Because it is not because we have two forces at the two sides. Because it is not symmetric velocity profile.
Yeah, but you told about forces also, no? Because
Yes, sir.
this altogether, this maximum velocity front will depend upon a drag force exerted by this
Yes, sir. Both
surface
the
and drag force exerted by this surface.
yes, sir.
So where it will be near towards this wall or near towards this wall? Which will be nearer wall? So,
So
so what do you think? Where will be the drag force more? Whether it will be on this surface or this surface?
on the inner surface.
Inner surface drag force will be more. Okay, and where it will be? It will be not at this center. Whether it will be towards this wall or towards this wall.
Towards the inner wall.
towards the inner wall. That is what, okay, so we'll see, we'll discuss that thing. Okay, so we'll now have this everything. Okay, so non-vanishing velocity will be Vz. There is only Vz velocity. Velocity is there only in Z direction. There is no R velocity because driving force is 0. There is no theta velocity because problem is symmetric around theta. It is not symmetric around R, but it is symmetric around theta. So there is no velocity in theta direction. Vr equals to 0 and v theta equals to 0. So this exactly similar to previous problem. In previous problem, we have only z velocity and v theta and vr will be equals to 0. So altogether shell balance approach, shell and everything will be similar as we have taken in previous problem. Exactly similar. So what will be the dimensions of the shell here? And Vz, whether Vz is the function of theta, R and Z. Vz is a function of theta, R and Z. Here roll number 93, Sai. '93. Roll number 110, Tanmay.
Yes, sir.
Yeah.
Sir,
Say-
velocity will be function of r, like we saw in this at boundary conditions. On those boundary conditions, on those two boundary
Yeah,
conditions,
velocity is
velocity
the
is
function
0.
of R. Velocity is the function of R. Why velocity is not function of Z? Tanmay. Why velocity is not function? Why velocity is not taken as a function of Z in this problem?
Like in the previous case, we had the symmetric flow around it.
No,
So
Z, Vz. Why Vz is not changing in Z direction?
sorry, sir. Like the mm, for the theta.
Huh?
Like sir, the force, we have to use the continuity equation. Like in the previous case, also we used the
Because
continuity
the
equation for that.
flow is continuous and incompressible flow. Okay, flow is continuous and incompressible. Hence, so cross-sectional area and closed boundary problem. This is closed boundary flow. So this flow is governed by this inner boundary of this cylinder and outer boundary of cylinder and inner boundaries. So this is closed boundary flow, continuous equation, incompressible fluid. Hence, so continuity equation will give me Vz is not function of Z, even though there will be some variation at the start and at the end there will be some variation, so I can neglect the end effects. End effects are neglected and problem is fluid is incompressible and continuous flow. These are the three reasons why Vz is not considered to be a function of Z. Why Vz is not function of theta? Roll number 106, Swapnil. Swapnil. Roll number 109, Sashank.
Yes, sir.
Why Vz is not function of theta?
Sir, it is symmetrical around the pipe.
Very
That is the reason
symmetric
the
around
difference is very
axis.
small.
So
Is theta
symmetric around
axis.
axis of the pipe is at the center. So problem
Yes.
problem is symmetrical with theta in theta direction around this axis. Problem is symmetric. Hence, there is no variation of velocity in theta direction. Okay, Vz is a function of r only. So, what will be the dimensions of differential shell? Roll number 111, Vipasvi.
Yes, sir.
What will be the dimensions of the differential shell? Differential shell.
Sir, the differential shell will have a the radius will vary from
R2 R plus delta R.
Very good. Differential thickness in R direction and
Yes, sir. dr will vary from R to R plus delta R, and the length will be varying from L, like in the Z direction, from 0 to L.
why total length you are taking? Why differential thickness is taken in R direction?
So because the velocity is a function of R.
Very good. And velocity is not function of Z. My properties are not changing in Z direction. In total Z is taken. How about theta? What are the
Sir,
boundaries of theta?
so theta will vary from 0 to 360.
360. So differential will be exactly similar as we have done in previous problem. Flow through pipes. Okay. So this is what input from the problem. So hope you have read the problem carefully from Saturday to from Monday to today. So this is our input given in a problem. Okay, and pressure is a function of Z. As I am moving up, so pressure there is a change in pressure. So because of that only there is a flow. Okay, so this pressure is a function of Z. Now this is kappa R. Okay, what is kappa R? This is the outer radius of the inner tube, kappa R, and this is inner radius of the outer tube. And I am discussing flow in this region. The flow in this region is discussed. So this is symmetric around theta. So whatever be the flow characteristic here, it will be symmetric around theta. So same flow characteristic will be in this region also because it is symmetric around theta. So theta is round, so it is symmetric. So the flow is between kappa R and R. So this is the flow direction. You can say flow is in upward direction in this annular region. So now here velocity is 0. This is no slip boundary condition because outer tube is steady. So velocity is 0 at this interface. Similarly, velocity is 0 at this interface. So here velocity is 0, here velocity is 0. Certainly this will go through maximum velocity and reaches the 0. Initially it will increase and decrease with respect to R and negative R direction also. Here also it will increase and decrease, but this maximum velocity front will not be at the center because whatever be the drag force or resisting surface, okay, area of the resisting surface is not same. Inner surface area is smaller, okay, surface area drag force exerted on by inner tube will be a, you can say twice pi kappa R into L, and while outer it will be twice pi RL surface area. This surface area is not same. As this surface area is not same, so certainly it will not be symmetrically. The forces are not acting by both the forces or drag force exerted by this. Both the surfaces are not same, so maximum velocity will not be at the center. It will be off center, and wherever there will be maximum velocity, there a shear stress will be 0, and from there the shear stress or momentum flux will be in a direction of decreasing velocity front. So this will be say maximum velocity front. It will not be at the center. It will not be at the center. It will be away from the center towards the inner wall or outer wall. So that we will see. And this is say lambda r. Some lambda r is there. Say kappa equals to 0.75. So lambda will be between kappa and 1. Kappa will be between 0 and 1. Kappa will be between 0 and 1. So it cannot be 0, it cannot be 1, it should be between 0 and 1, and lambda will be between kappa and 1. Okay, kappa and 1. Say for example, outer this diameter of this pipe is 1 meter. Say this will be some 0.75 meter, and then this will be something around 0.8 meter, 0.85 meter or so. Okay, this will say lambda r. So the momentum flux. So here I will have maximum velocity front, and momentum will be transported from maximum velocity to a lower velocity front. Okay, so there will be momentum flux moving in r direction if my if I'm considering region between lambda r and r, if I'm considering the region between lambda r and r, momentum flux will be in a direction of r. If I'm considering the region between kappa r and lambda r, then momentum flux will be in negative r direction. Okay, this will be the direction of momentum flux, because here I will have maximum velocity front and velocities are decreasing. Momentum flux will be in a direction of decreasing velocity only. So if I am considering a region between this lambda r and kappa r, so momentum flux will be in a direction of r. While if I consider this region, a region between kappa r and lambda r, the momentum flux will be negative r direction. So negative r direction. So why? Because again velocity is decreasing as r is increasing. So now I can this is say you can say. So it will be slightly towards the inner surface. Okay, this maximum velocity front will be slightly towards the inner surface, because the surface area of inner tube, outer surface area of the inner tube is smaller than inner surface. Hence force exerted or momentum flux exerted by shear stress exerted by this surface will be more. Okay, this surface will be more as compared to this. Hence maximum velocity will be at somewhere between this center and kappa. It will be towards this inner wall. So this is what the expectation of velocity profile, and this is what the shear stress will be there, momentum flux. So this is momentum flux. Okay, maximum velocity front. Here you will get a zero momentum, and here you will get a highest momentum flux, and here you will get a highest momentum flux. Okay, here you will get a highest momentum flux. So it is on upper side and lower side. It is indicating that this momentum flux in a direction of r, and this is the momentum flux in a negative direction of r. Okay? Even though that magnitude itself is important, magnitude of the momentum flux is important, but this is just a representation. Okay, previously it was symmetric around theta. Okay, symmetric around r also. So everywhere else. So now with r initially with r you will get maximum momentum flux, and increasing the value of r it will go to 0, and then again it is increases. So this is in positive r direction, this is in negative r direction. This is the now after solving couple of problems you should able to expect this velocity profile. This is very important. Expectation before getting any answer. In modeling, whenever you are modeling anything in any subject, you should expect the output. What kind of output you are expecting? Okay, so like if you are conducting variation of kinetic constant with temperature. So with Arrhenius law, you should expect that kinetic constant will increase with the temperature. Similarly here also, so this will be the velocity profile. Here velocity profile is 0. Here velocity is 0. Here velocity is 0. Maximum velocity will be towards the inner surface, and so this will be the kind of velocity profile. And then here velocity is 0 means flux will be, here velocity is maximum means flux will be 0 at this you can say lambda r, at this lambda r line. So flux will be 0, and here in this region there will be momentum flux in positive r direction. Here there will be momentum flux in negative r direction, and I will get a maximum momentum flux at r equals to kappa r, and maximum momentum flux at r equals to capital R. So this is expectation is very important. What kind of expectation you are getting, then you can solve the problem very easily. Now here only the thing is, now if you take the shell in this region, now you can take in this region between kappa r and r, kappa r and lambda r. You can consider a shell in this region also. You can consider shell in this region. What will be difference between these two? If I take a shell in this region and shell in this region, whether there is any difference? Roll number 88, Pratish.
Yes, sir.
Yeah. if I take a shell in this region, whether there will be any difference. This is what I am telling. I can take a shell in this region. R varies from R to delta R. And this is also my region, okay? So I'm taking this region. R varies from R to delta R. This is my region. Whether there will be any changes here?
Sir, in terms of velocity, if we see like this type, in considering this, if the shell is from R plus delta R and towards the left side of R, so there would be more velocity. But if we take this,
But
the
how
integration,
you will account for this?
like we have seen it in the previous thing, with the account of shear force. Like the stress is more in the outside direction, so the velocity is.
Okay, but where it will make a changes in modeling? Which step? So you can see here, velocity is increasing with R. Okay, velocity is increasing with R.
Yes.
Okay, and here, velocity is decreasing with R. So which step need to be, where it will be considered velocity is decreasing with R or increasing with R?
So while applying the limits on that integration,
Limit.
yes, sir, like when we would be integrating that thing, like taking that shell to an entire range, at that point we'll have to change it, the sign of integration.
Sign of integration.
So like we'll set the limit as R to lambda R and then lambda R to capital R.
No, how can you set the limit, man? Lambda R is just a velocity front where you will get maximum velocity. That is not a boundary.
Okay, sir.
Roll number 1, Abhinav.
Yes, sir.
So where you will account for this?
Sir, in minus sign, I guess.
Where minus sign?
Tau.
Yeah, very good. That is Newton's law of viscosity. Okay. So if I am considering this region, velocity is increasing with R. So it will be mu dV by dr. Okay. If I am in this region, so it will be minus mu dV by dr. Because velocity is decreasing with R. So dV by dr is negative here. So I will be adding minus sign here. So I will be adding minus sign here, while in this region I need not to add the negative sign. But overall, you need not to consider this. Take a shell in this region or in this region. What will be the difference is you will get a different value of constant. So my boundary varies from kappa r to r. So only the thing is constant are different if you add negative sign or don't add negative sign. Constant will be different. Ultimately, model equation will be same. So we'll be considering same. Velocity is decreasing with r. Velocity is decreasing with r, and we'll take a similar assumption that minus mu dv by dr. So you go home and try with this. So ultimate model equation will depend upon a boundary condition. So this is my one boundary. This is my another boundary. What different you will get? You will get a different value of constant, but ultimate model equation will be similar. So you go home and solve for this. Okay. So we will be solving for this. So once I consider this, velocity is decreasing with r. So it will be exactly similar. Okay, exactly similar to previous problem. Now go to previous problem, flow through pipes. So you can consider. So here we'll be taking only r momentum balance equation. Only r momentum balance equation is taken. Momentum balance for r, not r. So it will be Vz. Okay, momentum Vz momentum balance is taken because we have velocity in z direction only, and differential thickness will be taken in r direction. Okay, so z momentum balance only will give me a velocity profile equation, and this will be exactly similar as we have done in previous problem. Only here g, okay, g instead of g, what will be your force acceleration due to gravity in this case? So gravitational force acting in z direction or in a direction of flow. What will be gravitational force acting in a direction of flow? Rule number 21, psi.
Yes, sir.
What will be the gravitational force in acting in a direction of flow in this annular flow?
Negative direction, sir.
Negative direction. So instead of g, I need to take minus g.
Yes.
Other thing will remain same. This is the rate of z momentum coming in across the surface at z equals to 0. This is the rate of momentum coming in the differential shell across the surface at r, in r direction. This is in z direction. Theta is actually surface theta is matching actually, and that momentum is also 0. So this is the rate of momentum out across the surface at z equals to L. This is the rate of momentum out across the surface at r plus delta r. This is momentum in, this is momentum in, this is momentum out, this is momentum out, plus generation and consumption of the momentum, which will be governed by external forces acting on my differential shell. That will be twice pi r delta r into L rho g. So instead of g, I will have minus g actually, minus g. So rearrange this equation, rearranging the equation minus g for minus g, and so do everything same thing. Only the difference is you put minus g here and rearrange the equation. After rearranging the equation and substituting all this, okay. So what you will get? This is the definition of modified pressure in this case. So modified pressure will be P0 plus rho G0 and minus P plus rho GL. So what is why this is plus sign is coming in here? Because potential head is increasing in Z direction. As I am moving in Z direction, potential head is increasing. As I am moving in Z direction opposite to gravity, so potential head is increasing, hence this positive sign is coming. Okay, so only this is the difference what you will get, otherwise it will be same. So P0 minus PL divided by L into R del by del R of this thing. Okay, this is exactly similar. So just try to solve this, rearrange the equation and see whether you are getting this positive, you are able to get this rearrangement. P0 plus rho G0 minus PL minus rho GL. Anybody is not getting, just let me know. Once you got this, okay, only why this is plus sign is coming in here. Plus sign indicates the potential head of the liquid is increasing in Z direction. As I am moving in Z direction, the potential head of the liquid molecule is increasing. Try to rearrange this. Only the difference is actually, as that of previous problem, you need to take minus of G. Minus of G, forces acting, gravitational force acting in Z direction or in direction of flow. Flow direction is in Z direction, and this gravitational force acting will be minus of G. You take minus of G and do all this rearrangement as we have done in previous problem. Okay, so multiply it by minus 1, rearrange the equation, take out this rho G this side and rearrange this equation. Okay, rearrange this equation and then substitute the definition of phi rz and phi zz. So phi rz will have three components. One will be a molecular momentum flux because of pressure forces, another will be molecular momentum flux because of viscous forces, and third will be a convective fluxes. Okay, similarly this also will have three components. Okay, pressure forces and molecular flux because of pressure, molecular flux because of viscous forces, and third one will be convective. Substitute this definition. This is what I am telling. Okay, this will be molecular flux because of pressure forces, this will be molecular flux because of viscous forces, and this will be convective fluxes. So this here you will not have P, because P into delta Rz will be delta Rz equals to 0. Here delta Zz will be equals to 1. And now you can substitute this actually, and tau zz will be equals to 0 as there is no variation of velocity in z direction. This will be equals to 0. So rearrange the equation and substitute the definition of generalized Newton's law of viscosity. Exactly same what we have done in previous problem. And after rearranging the equation, you should get only the difference is here you are getting positive sign. In previous problem, you got negative sign. Here you should get positive sign after rearrangement, and in previous problem you got negative sign because that was gravitational force is that acting in a direction of flow. Here gravitational force acting in opposite direction to flow direction. So potential head is increasing as I am moving in a z direction. Their potential head was decreasing. Potential head was decreasing as I am moving in z direction. If you get this equation, you can write S in chat box. If anybody is getting any difficulty in getting this equation, just let me know. Anybody got this rearrangement? Anybody got this equation after rearrangement? You can write in chat box, yes or no. Okay. Yeah. Anybody not getting this equation or got any confusion in a discussion what we had till now? Anybody not getting this equation? So this is the one difference between previous problem and this problem. One difference, that is that flow was in a direction of gravity. So, and this flow is against the gravity. This is one difference. So anybody is not getting this equation? Okay. So this is the equation what we got in previous problem also, this problem also. After integrating this equation, tau Rz will be equals to P0 minus PL divided by 2L into R plus C1 divided by R. So this is what equation we'll get. Now this, for getting this one constant C1, I need a one boundary condition with respect to tau Rz. So whether I have that boundary condition available in this problem, or what is the boundary condition we have used in previous problem? Roll number 36. Yes.
Yes, sir.
So what is the boundary condition we have used in previous problem to get the value of C1?
Sir, no slip condition that tau is 0 at R.
That is called no slip condition.
So
Tau
at the
is 0
boundary,
yeah.
so at the boundary at R equals to 0, no, that's for velocity, sorry, sir. So, at R equals to,
So yes, can you share your notes you are writing in a class during class? Please share your notes. Switch on your camera first of all.
yes, sir.
So some people are leaving the meeting when I ask the question. It seems that I'll be taking it as a
So my camera is visible.
just hold on. Stop my sharing. Not it. Your camera is not visible. So if you are leaving after asking the question, so I'm considering that you are not able to answer this and wrong answer. That is also noted down. And if somebody is leaving, okay, yeah, okay. Now I can see. So can you go to this previous problem where we got similar thing?
The previous problem. So last problem I have not written, but shell momentum balance I have written, sir.
Where is previous problem?
After shell, so floor that I am not written, sir.
Okay. Yours is 36, na?
Yes, sir.
Okay. Yeah, roll number 55, Somesh. So what is the boundary conditions we have used?
Sir, am I audible?
Yeah, you are audible.
Sir, we can use maxima that at maximum velocity, stress is 0.
So what will be the boundary condition here?
Sir, at r equal to lambda r, stress is 0.
But lambda r is where is lambda? What will be the value of lambda? Okay,
So we
kappa
can
is
calculate.
known. You can measure the inner boundary, inner radius of the cylinder, radius of inner cylinder, that will give you kappa, and radius of outer cylinder. What will be the value of lambda?
So we can calculate it further at velocity.
How can you calculate? You don't know velocity profile currently.
So we can put the
Okay,
value
what
of
is the boundary condition we have used in previous case?
that previous case we use logical boundary condition.
Okay, logical. What was that logical boundary condition?
So at like in previous case at the center, uh, stress has a finite value.
Okay. So that was the boundary condition which we have used in previous problem. At r equals to 0, tau rz should be finite. Okay, but that boundary condition we cannot use here. Okay, that boundary condition we cannot use here. Look, lambda was not given in a problem. So now from here there are two ways to solve the problem. First of all, assume some value of lambda. And what is value of lambda? What is lambda? At lambda r, at r equals to lambda r, velocity is maximum. And hence at r equals to lambda r, tau rz equals to 0. That is one way to solve the problem. And then at the end, when you get the velocity profile, you can get lambda in terms of kappa. Okay, what is given is kappa r and capital R. Lambda r is not given. Lambda r is not given. I can assume some value of lambda. Some value of lambda is assumed such that at lambda r, velocity is maximum. Velocity is maximum. Maximum means maxima condition we can use. Tau rz will be 0 at r equals to lambda r. That we can do. And then we'll go further in this problem and get the velocity profile. After getting velocity profile, you need to get the value of lambda in terms of kappa, because kappa r and r is given, lambda is not given. That is one way. Another way is saying that I don't have flux boundary condition, because at r equals to 0, I cannot use this boundary condition. At r equals to 0, tau rz equals to finite. Whether I can use this boundary condition? 61, Rutvik?
Yes, sir. Yes, sir.
Whether I can use this boundary condition at r equals to 0, tau rz is finite?
No, sir.
Why?
Actually, sir, we have used in it previous case that at r is equal to logical
In
condition.
previous problem, why in this problem I cannot use at r equals to 0, tau rz equals to finite?
Tau rz is equal to finite.
At r equals to 0.
Sir, logically thinking that there is no liquid flowing through that area.
What you told?
There is no fluid flowing through that area. It's hollow.
Actually, we are considering flow through annulus. So my
Yes, sir.
geometrical boundary started at kappa r. At r equals to 0, that is not my area of concern in this problem. My area of concern is starting at r equals to kappa r and ends at r equals to capital R. So that logical boundary condition I cannot use. And second way is you can assume lambda r such that at lambda r this equals to 0, tau rz equals to 0, velocity is maximum, and then get the velocity profile and get value of lambda in terms of kappa. Otherwise, don't do anything. Don't substitute the tau rz boundary condition, and straight away you can go in a using Newton's law of viscosity. You use Newton's law of viscosity. So this none of this boundary condition can be used here. So I don't have say liquid gas plane or logical boundary condition. This cannot be used. Okay, liquid interface is not there. Liquid fluid interface, no slip condition is used only for velocity. So I cannot use any of these boundary condition. So as this cannot be used, I will be using Newton's law of viscosity in this equation straight away. So using Newton's law of viscosity and integrating the equation. Using Newton's law of viscosity and integrate this equation. So this C1 is as it is here. C1 is as it is here. So integrating this equation, rearranging the equation and integrating this equation, this is what I will get the velocity profile equation with two constant. Now to get this two constant, I need the two boundary conditions. What are these two boundary conditions? Whether I have two boundary conditions for velocity. Roll number 6, Aksh. To get these two constants, I need a two velocity boundary condition. Whether I have two boundary conditions for velocity?
Yes, we can use v equals to kappa r, r equals to kappa r, that would be velocity equals to 0. And also r equals to capital R. And at that place also velocity would be equals to 0. So we can calculate these two constants then.
Okay. Okay, so both are mostly boundary conditions, solid fluid interface. So what is this? At r equals to capital R, velocity equals to 0. So if I substitute r equals to capital R, this is the equation I will get. Okay. Now at r equals to kappa R, at r equals to kappa R, velocity equals to 0. Substituting this is equation 2. Now this is equation 1 and equation 2. Using this, you get the value of C1 and C2. Substitute in this velocity equation C1 and C2 and get the velocity profile equation. Okay, everybody got this point? And what is another way? Another way to solve this problem is assume some value of lambda. Okay, assume some value of lambda between kappa r and r, between kappa and 1, some value of lambda r where velocity is maximum, and at r equals to lambda r velocity is maximum. It means that at r equals to lambda r tau rz equals to 0. Substituting that, get the value of C1, then substitute Newton's law of viscosity, and then get the value of C2 using any one velocity condition, no slip condition. Now using another velocity condition, you need to get the value of lambda in terms of kappa. Okay, better than that, you solve with this method. Okay, now don't I'm taking this C1 as it is for further processing. Okay, this is the velocity profile equation I got in terms of two constants, C1 and C2. This is the integration constant from differential equation, and this is the integration constant from a Newton's law of viscosity. Okay, two constants are there using this two boundary condition. So this two boundary condition, I will get this two equation. Now rearrange this equation and get the value of C1 and C2. Substitute in this equation and get the value of velocity profile. Okay, you try this problem at home and we will discuss this problem in continuation in next class tomorrow at 10 o'clock. Okay, you can view the class if anybody has any doubt.
Excuse me, sir.
Yeah, tell me, Aksh.
Sorry, sir, it's Aditya.
Okay, Aditya.
Sir, we introduced one term like drag force while we were discussing about the velocity profile in annulus region, right?
Yeah.
So, can we also say this no slip boundary term, the layer which is on the outer cylinder that has greater area, so it will restrict the motion of first layer of water more than the smaller cylinder inside smaller
That is
cylinder.
what momentum flux is there, no?
Yes, sir, that's what I was asking. Can we write no slip also, like we said, drag force, we correlated it with the area, like difference in area. So can we introduce the no slip boundary term also while explaining this kind of thing?
What exactly you are telling? I'm not getting.
Sir, actually, what no slip boundary condition means, the velocity will be same as of the solid, like liquid's velocity will be same as of the solid. So the here solid is in rest condition, so the first layer will be having zero velocity. So the outer cylinder is bigger. So the first layer of the water which is in contact with the bigger cylinder will have the zero velocity, but that's the what we can say, the bigger layer, and the layer which is in contact with this inner cylinder, that has a smaller layer also having the zero velocity. So
No. This is no slip boundary condition means at interface.
Yes, sir. Yes,
Both
sir.
layer will have same radius at interface.
Okay.
That is not, you can think of, and that variation in R is very small. No? It will be in angstrom.
Okay.
How to account that physically?
Okay, sir. Okay. No, sir,
And
like
this, when I am saying that it is at interface, so you can say solid fluid interface.
Yes, sir, matlab, ultimately it will start
Yeah,
from zero and end
ultimately
to
it will be
zero.
last layer of solid and first layer of the fluid. But this is at interface, so I cannot differentiate value of radius.
Okay, sir.
But what intent you want to get out of that? Assuming different radius.
Sir, like bigger radius will have bigger area, restricting more motion of the liquid, and smaller cylinder having smaller area, restricting lesser lesser
No, no,
layer
no,
of.
no, no, no. That cannot be considered actually. That is wrong assumption. So we are assuming the first layer of the fluid in touch with solid will have velocity of solid because this is at the interface. Now fluid cannot have so much viscous forces that solid molecule will start moving. This is not at all possible that fluid viscosity is so high that that solid molecule will start moving. That is not at all case. So certainly at the wall, the fluid velocity, fluid molecules will not move because this is at the interface. So you can say same. This is last layer of solid is equals to first layer of the fluid. Equals to, that is equals to. That is inseparable. So that is interface.
Okay, sir, but like in the very first class, you explained with the molecule, like you took 7 molecules, and the
Yeah,
lowest
but
molecule
that
was.
is in liquid. That is in liquid phase. Phase is not changing there.
Okay, okay, sir.
That is phase is not changing there. That is why we got this interface flux also. That they are all together. All logic will be different actually.
Okay,
That
sir.
is in same phase if I am moving. That time I can discuss that actually. Molecule to
Maybe
molecule.
I'm not able to explain you my doubt properly. I'll try to find some other language how to put it, then I'll ask
Okay,
you again.
okay, 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 okay.
Okay, sir.
You just
Thank you.
think over this, and maybe with figures and all, you can put your doubt. Then we will discuss. Okay,
Yes,
either
sir.
you can discuss. You can call me some other time also during class time also. We can discuss.
Yes, sir. Thank you. And sir,